Hello. So this time we'll consider a linear transformation that we have seen before. But now we are going to find a spatial representation of this linear transformation. Now, there's a different way of justifying that this function is indeed linear, and it's by actually constructing this as a product of a matrix. So how so? Well, it's not so difficult. If we just inspect the element that we have here, note that we may represent x plus y, x minus y, to x plus 3y simply as 1, 1, 1, negative 1, 2, 3 times the vector xy, right? Which indeed would be that this is t of xy. And why is that you're saying, well, why is what we're saying that this is a linear transformation without the going into the actual definition and demonstrating it like we did it last time? Well, it's based on the following idea. Since matrix multiplication distributes over matrix sum, and scalar multiplication commutes with matrix multiplication, we see that in general each transformation of the form t of x being equal to a times x, where a is a matrix, is linear. Right? This is enough. But, well, the question now comes in the opposite way, right? Is every linear transformation of this form? In other words, can we find a matrix representation for each linear transformation? Well, we'll go into details so that we can actually determine a mechanism to find such a representation, and we're going to explore the example that we have. So our example looks like this. Note that we may write t of xy as being decomposed into the coordinates of the input to this function. So t of x times 1, 0 plus y times 0, 1. You may wonder why. Well, these are exactly the coordinates of the vector xy in the standard basis of R2. I'll put it in details. The coordinates of xy in the basis written in this particular order, 1, 0, 0, 1, are x and y respectively. But well, but t is linear. So we have that t of xy is equal to x times t of 1, 0 plus y of t of 0, 1. Well, what are we saying here? The action of a linear transformation is completely determined by its action on a basis of its domain. So, all the information that we need to capture the essence of the linear transformation is to see how it behaves on a basis. Well, let's see how it behaves on a basis. Let's actually determine a decomposition or a representation of t acting under the standard basis of R2. So we'll decompose it. T of 1, 0, and well, it's nothing else but 1 plus 0, 1 minus 0, 2 plus 0, which is now 1, 1, 2, which is nothing else, right, but the coordinate vector in the standard basis of R3, right? How so? Well, because I can decompose it as 1 times 1, 0, 0, plus 1 times 0, 1, 0, plus 2 times 0, 0, 1. Okay, now for the second basis vector applied under the action of t, let's see how this behaves. So this should be 0 plus 1, 0 minus 1, and 0 plus 3, which of course we can rewrite as 1, negative 1, 3, which of course we now can decompose as 1 times 1, 0, 0, plus negative 1 times 0, 1, 0, plus 3 times 0, 0, 1, which here we are indicating the decomposition of that vector in the standard basis of R3. So, well, let's compile everything that we have here, and we see that T is represented by the following matrix: 1, 1, 2, 1, negative 1, 3. But each of these columns that we're writing here have an interpretation, because this one, it's really the coordinates of T of 1, 0 under the standard basis. This one, well, analogously, represents the coordinates of T of 0, 1 under the standard basis. Now, if you want to actually represent the action of this matrix, well, we can see it in this fashion, right? I'm going to make a small note on the side, right, associated with this. And we have, well, how do we see T of U, right? Well, T of U is given in this representation by the following. We have 1, 1, 2, 1, negative 1, 3, times U1, U3. Of course, we perform the actual matrix product, and this turns into U1 plus U2, U1 minus U2, and U2, U2 to U1 minus 3, U2. Well, let's give some meaning to this, right? This one is the representation of T. This one corresponds to the coordinate vector of U. in the standard basis. And what will be this? Well, that's the coordinate vector of T of U. In the standard basis, of course. So now we have a different way of seeing linear transformations. They are transformations that take coordinates to coordinates. You may wonder, what happens if we change the basis? Would that change the representation? Of course. So stay tuned for the next video where we see such a situation. Take care.